All right, let's get started. Welcome. Robotics 311, lecture 17. Getting up there. Today we're going to do a few things. I'm going to talk a little bit about lab yesterday, show you a plot, what you guys should get. We're going to discuss wheels, so Omni wheels and mecanum wheels. And then we're going to break for you guys to work on both yesterday's lab and the homework, so to give you time actually working on your ballbots. And I think it might be that we do class like a little more in a hybrid mode. I feel like you're not getting enough time to work on your ballbots. We're spending a lot of time going over content. We've made a ton of progress in that content, but we're spending like some time working on ballbots, but it's usually a struggle. And that's the whole class is supposed to give you that skill. So I feel like right now we're not achieving that. So we're gonna break kind of like halfway through today. We might do ballbot work instead of lecture on Tuesday. Lecture next week. On Thursday we'll review. So if somebody asks for review, I'll do that review next Thursday. The following Tuesday, I think it's Tuesday is your exam. Is that the 8th? Is it the following Tuesday? Okay. So we only have one more lecture if we're gonna do review before the midterm, and I haven't decided yet, but I think I might just give you that time to work on your ballbots. If we do ballbot working time in class time, would you guys rather do that here or do that in the lab? The lab is easier? Okay, I think the lab is available. So if we ever meet there, I'll have to make sure an announcement gets sent. So plan to be here unless you hear an announcement, yeah.
Are we allowed to bring an equation sheet to the midterm with like some of those like complex equations from earlier? Or
you won't be able to bring an equation sheet, but it'll either be open note or I'll give you an equation sheet. But whatever it is, you guys will all have the same thing. That's my current plan. If it's open note, would that be too challenging, do you think? I'm leaning towards open note. I have to make this exam, but I'm leaning towards open note. There's a lot of notes for this class. So that means like in real time, you're having to go through those notes. Does that seem feasible? Is that how you guys would want to do it? Like what would be the best way for you guys to feel most equipped for the midterm? What do you think?
Are we allowed, like if we have like I take notes by like using like these like lecture like slides, and would I be allowed to have like my notes on the lecture slides with me, or?
That's a good question. I think it would be hard for your notes to be better than my notes. My notes are awesome. The ones that I post, the full notes are very detailed.
Oh, you think we could use those then?
It would be the full notes, not the blank
okay.
notes.
I thought you meant like only stuff that we copied.
No, as far as I'm concerned, you guys should really be looking at the full, complete notes. Those are the ones that have all the content that I think is most important. I usually speak that content, what's not written down, but I would say if you're looking for material, use the completed notes. Yeah.
So if it's open note, then will we only get your slides, or could we like reformat the notes and bring them in?
I would probably reformat them for you.
Okay.
With like topics maybe, or like the subject, because like they just say like lecture 17 versus like the actual what it's covering.
I probably wouldn't do topics, or maybe I could do topics, but I'd probably do multiple slides per sheet. So you'd be able to, it wouldn't have to be 100 pages of notes. It would be something like that divided by 4. Yeah.
Student created cheat sheets, so I like those a lot.
The problem with student created sheets is there's so much content that I feel like that's going to put you in a difficult position. Because, like there's so much content. Like normally I would be able to, if I had made the exam before, or we had Todd's class before, I would be able to tell you these are the kind of specific styles of questions you'll be asked, which would make that more tractable. But without that, I feel like I'm open to it, but I feel like it's harder for you guys. Yeah.
I kind of agree with him because I always find that a really powerful way to study, and that process of compiling your own cheat sheet is
helpful. You can do that either way. You just but in terms of preparation, you can still do it. Yeah.
Do you know the format of the exam?
I suspect, I don't know because we haven't made it. We're going to make it kind of over the next 2 weeks. My guess is it'll be something like a multiple choice section. So like 10 questions, multiple choice. Then probably 3 or 4 kind of detailed questions where you work them out. Like a paper and pencil style question. My guess is they'll be somewhat similar to the homework, but usually faster and more targeted questions. because we don't have the same time. So that's my current thoughts, but yeah, like this can be a discussion. Like I want to test you guys on the material you've learned, but exactly how that goes can be a discussion. So we have some time to think about it. But if you have thoughts, let me know. So like, it's good to know you guys would prefer to write your own cheat sheet, even though I think it's unlikely that we do that. And then I'll try to figure out a way to compile these notes, either topic, make them, like group them by topics, and compile them into a way that would be easily perused while you're under the gun. Cool? Okay, so then that brings us to like next week, Thursday is review. Tuesday is either going to be a lecture content where we lecture where we talk about control, or all about work time, and we'll push control till after the midterm. And then the control part of the class is really the class I think it's going to be part, hybrid format, because we're going to want to be doing that together, and you're going to want to be working with your ballbots a lot. So just one lab per week I think is not enough time. Cool? And the homework is like generally geared to push you into working more with your ballbot. Yeah.
I just have like a kind of question. It
Yeah.
has to do with like the lab from yesterday. Like I saw you posted the assignment, but there's no actual like submission.
Should have an online submission possible. If not, I just need to edit that.
Okay, yeah, because like I'm just on it. Like I don't even see like a
There's no submission portal. Okay.
not that I can see, but
I'll add it's like a checkbox I have to check when I create that assignment. Maybe I might not have done that. So I'll modify that. Thanks for the heads up. Okay, so lab. So we learned yesterday. You guys learned like how to set power or command torque to your motors, which we had not done. So until yesterday, we'd only read from them, but now we're able to send torque commands. The way that we did that is through this set of Python syntax that's in that script that you guys were provided. So we basically like set what they are. This is going to be their duty cycle, which corresponds to their torque. And then it gets set with that command there. So that's going to be how we're going to end up setting the commands to the ballbot motors. The goal for the lab was to have you like rotate this ball in a specific set of directions. And I said 8 to 10 directions around a circle. The goal for that is to make sure that you have control over your ballbot in the XY plane. That's what you're going to need to do this, the rest of this to be successful. So the way that we were testing this is I said, step around the circle with something like 8 to 10 torques, and then record the encoders during that motion while the ballbot's upside down, and then plot them together. And you should be able to get something that looks like this. And thanks to Blake for sending this. This is his plot. You should get a plot that looks like this. And this is sort of exactly what I was hoping it would look like. And what I'm kind of prompting you in the lab is to sort of talk about the difference in the black and the red. In this case, so the black is from the actual encoders, and the red is received from the torque command that moved it. So the red data is in Newton meters, the black data is in meters. So you should get a plot that looks like that. That's the game. That's what you should submit, is your version of that plot. If you can do this and your plot looks something like this, you have full control of the ballbot in the XY plane. That's what you need. Any questions about this? I've been thinking about, you know how the balls or the wheels are rotating slowly in your ballbots? And I hadn't seen that before. I want to talk for a second about why that is. It's not in the lecture notes, but it occurred to me while walking over here that I could talk you through that. So this is one thing that we've done in the firmware. You guys probably understand that if you apply a torque command to the motor, a really small torque command doesn't move the motor. Its internal friction just holds it in one spot. That internal friction we call stiction, static friction. So it's going to take some initial torque or duty cycle to overcome that. Then it's going to provide a pretty linear relationship with torque. So let's look at, I'm just going to draw this real fast. If we look at, let's see, maybe I'll call this theta dot, and this is I. It's going to do something like this. So you're going to have an initial part where as current goes up, nothing happens. Then you would see theta dots start to increase linearly with applied torque, or something along those lines. But this is what we're talking about, is this initial stiction part. So what we've done is take your command. So now let's think about like a duty cycle. Duty cycles are 0 to 100%. This is how we're providing our command to the motor. It means that a certain part of this duty cycle does nothing. Because that's the part of the duty cycle that kind of lives in this area. So within the static friction. Now imagine if we're trying to balance this ballbot, we're gonna often be trying to apply very small torques. That's gonna be an important part of the success of this ballbot. So what we've done is take your duty cycle command and remap it to this. So let's say this is this. Okay, so your first part of your duty cycle doesn't cause the motor to move or doesn't break static friction. So if you give a value that's small, we remap this value to live here. So we basically like delete this from the motor's duty cycle so that you're always operating, even with low torques, you're always operating with the amount of torque that will cause the motor to move. What that means is, depending on what where this threshold is set, there's now a new minimum duty cycle that's not 0. So the lowest duty cycle that you can provide is now like this value. That minimum duty cycle causes your motors to rotate. It only causes your motors to rotate when the weight of the ballbot isn't on them. That's why you're seeing it. It's because it's upside down or it's sitting like stationary on the desk. It's not in the ballbot configuration. So my guess is when we actually put it there, the ballbot on top, you won't have this issue anymore. The weight of the ballbot will take up that extra PWM duty cycle that's causing it to rotate. So then it won't be rotating anymore. Yeah.
I do know when I had mine wheels down on the table, it still just spun in the circle. I had all 3 motors going, so the weight wasn't quite enough to overcome it.
Yeah, this was sort of tuned on our ballbot. So it is possible that it still may be like a little aggressive, but we won't know that till we actually are trying it. If it is, we might update it to lower that PWM threshold so the PWM starts a little bit lower. We don't want it to be spinning for no reason. So we would update that if it didn't, when you flip it over, if it didn't stop. That would involve a firmware reflashing. So it is possible that we eventually have to tell you, hey, put this firmware on your Pico. Cool. Okay, so that's just a little bit about the lab and sort of explaining that slow rolling motion that you're seeing. Any questions on that before we move back to lecture content? All right. So this is where we were last lecture. We learned about quadrature decoding. And the purpose of quadrature decoding is to just understand the direction of motion. Counterclockwise or clockwise, and we do that by which pulse train is leading in this 2-encoder setup. What's another name for one of these pulses? We call it something else also. Or what unit is it in? Yeah. Yeah, tick or count. Yeah, those would be the same thing. So those are the counts. So counting the actual ticks that go by. And then what was the purpose of this index?
Show direction.
Say it again.
To show the direction that we're
The
spinning.
index tells us, it locates it with an absolute location mark. So it's relative until you pass an index, then you have some understanding of its absolute position around the circle. Does that make sense? So an index is used to kind of bridge a relative encoder to an absolute encoder. So we talked about counts. This is how we talk about encoders. We talk about their counts per revolution, if they're relative. Those are our digital ticks that go by. Sometimes encoders will also output, their positive A-B signals that show that, and then also their digital opposite, A0 and B0, That's used with a different style of encoder that just kind of amplifies the resolution that you have. Encoders are generally provided with motors. You buy them at the same time. Usually you specify them then, and then below is no different. So it tells us when we buy this motor, we're buying it with a 64 count per revolution encoder. A lot of people, when you guys were doing your lab yesterday, you were creating a radians to counts conversion. Almost everybody got the 64 and the 2 pi, but most people missed the other coefficient that has to be in there. What's the other factor that needs to be in that equation?
70.
What?
70.
The 70 to 1. The transmission ratio. So this tells us the motor's count per revolution, but the wheel will have 70 times that because of that transmission ratio. And then I wanted you to find, last lecture I wanted you to find the color of a pinout, which you guys did. You found it in the data sheet. It looks something like that. This is sort of I like this as an example because it's kind of a graphical, pictorial version of locating a pinout. And like locating a pinout is something that we do a lot. If you guys, maybe let's pause for a second and do something with your computers. So if you guys, we talked about this BlinkM LED. You guys have one. You guys will be able to wire that to your ballbots if you want. To do that, you're going to connect wires to communicate this BlinkM LED to the Raspberry Pi. I want you to go online and find the pinout for the Raspberry Pi. So basically, like, I want you to tell me how you would connect this BlinkM LED. You guys have Raspberry Pi 3s or 4s? 4s? Who's got it? We're looking for the pinout for the Raspberry Pi 4 header. I found the Model 3 one, which I'm going to pull up.
Be the same, wouldn't they?
Hmm?
Wouldn't the 3 and the 4 be the same?
They're probably very similar, if not the same.
Close to.
Thank you.
So if you're searching for the pinout, you should get something that looks like this. Did you all get some version of this kind of diagram? Okay, awesome. How would you connect? The BlinkM LED operates on what digital bus?
I2C.
I2C. What are the names of the I2C bus lines?
SDI, SCO.
SDA and SCL. Where would you connect them?
3 and 5.
Which one?
3 and 5.
3 and 5. Yeah, so this says SDA1, I2C, SCL1, I2C. Is there a second bus?
SPIO.
No, a second I2C bus. I don't think so. There used to be, and rather there's 2 buses, 2 I2C buses. You can run them together. Does this make sense? This is like find a pinout. So if we were connecting our BlinkM LED, we would need to connect pin 3 to the SDA to data line on the BlinkM LED. We'd connect SCL pin 5 to the clock line, and then we would use power, either 3.3 or 5 volts, and ground. Those are the 4 wires. Yeah.
So if you have 2 devices that use I2C, like digital communication, you can only like use one with this Raspberry Pi. Like say I had 2 BlinkM LEDs,
Yes.
I could only use one.
No. So let me come back to that. We have a slide. I think I have a slide on I2C. I'll get back to that. So this is kind of like describing pinouts This is how you learn how to connect things together. So we did that for the encoder. That was like a kind of a pictorial example. This is the non-pictorial example. Okay. Good. Now we're on to communication. Talk more about the addresses. And this was reminding you guys like where we were. So we've done like all these things. We're kind of like here in this process. If you were building a robot, you generally have to sort out all of these things. And then I'm kind of like hoping for you guys to begin to see, like, oh, this class is called Build a Robot and Make It Move. Like now I can see how I'm learning to do that. This is how we have our system set up, our mechatronic architecture. We have our 3 motors sending their AB signals to the Raspberry Pi Pico. The Pico is counting those counts, sharing that information with the Raspberry Pi. I think it's over RS-232, but it's some serial communication that's established by Robotics when they built this setup. And then we have an IMU that's communicated over I2C with the Pico. So now we have an I2C bus the Pico is running. And if you connect the blinkum LED, you'll have an I2C bus that the Raspberry Pi is running. So you'd be running 2 different buses at the same time. Questions on this? Like, this is your time to stop me if like something I'm saying doesn't make sense. Yeah.
Can 2 I2C devices run on the same bus?
Yes. So I2C. So we're gonna that's I think the same question. So let me get back to that question in 1 second. We're getting to it very, very soon. One slide. Okay, so we talked about 2 different buses, SPI, I2C. You guys still have your pinout open of the Raspberry Pi? Find a 3rd bus. Yeah.
I have a question actually about the Pico, like
Yeah.
the I2C. Like I just pulled up its pinout because I was curious. I see there's like I2C1, I2C0, and then there's a bunch of them. Are the ones that all have the 0 relate? Like that's technically the same bus, just with different pins?
Yeah. So like, it sounds like you're saying there's 2 I2C buses, I2C bus 0, I2C bus 1.
Yeah, and then there's a bunch of like pinouts, like all the blue that you see. I know it's far away, but like all the blue you see are the different I2C ones. So like pins 4 and 5 is I2C1 as well as 9 and 10. So are they shared or is this making new?
I think they're shared.
Okay.
And I think that because like sometimes these pins have multiple roles.
Mhm.
So it looks like those pins can take on those different, like there's a bunch of different buses, and then those pins can be changed or used either in parallel.
I
or-
mean, like, if something's on the I2C1 bus on pins 4 and 5, then also 9 and 10, would that be sharing the same bus, or they are unique buses?
If it's I2C1, they're both the same.
Okay.
So that's just multiple pins that do the same function on a single bus.
Okay,
I2C bus 0 is a different bus.
gotcha. Thank you.
Yeah. Well, yeah,
Is PCM a 3rd bus?
not that I know of.
Alright,
27.
What?
Pin 27.
What is it? What's the name of the bus?
SDA 0 I2C.
That's I2C. So like that we have on there. So the Raspberry Pi, the pinout shows an I2C bus. It'll shows an SPI bus. And then I'm saying there's another bus that we haven't talked about. I just want to see if you guys can detect it. Yeah. UART is the name of the other one. UART is another bus that the Raspberry Pi has access to. Yeah.
I'm also saying TXT and RXT, which is CAN bus.
No, it doesn't have, Raspberry Pi doesn't have a CAN bus on it. TX and RX are just usually that's the general serial names for receive and communicate, like talk and communicate, talk and receive. Okay, so we talked about these 2 buses. There's other buses, USB, UART, but we're only really gonna talk about I2C and SPI, those are the most common. And I2C has these 4 lines, SDA, SCL, and power and ground. Now let's answer your question. So this is the I2C communication structure. What is the first thing that's sent? The address. And what does that address signify? Who on the bus is being spoken to? So the bus can have a lot of different ICs on it, different integrated circuits. So somebody who's being spoken to, first their address comes. How many bits is that address? 8 bits. How many I2C chips can be on one bus line?
256.
255, yeah, 256. So that's your answer. How many different chips can be on one I2C bus? 255 is max. That would be every address is used. So let's say we had multiple BlinkM LEDs that we wanted to add. So I don't know if you remember, when we were looking at that data sheet for the BlinkM LED, one of the commands was a software command to change the I2C address. So if you wanted multiple LEDs, you would have to change their addresses. So the addresses can't be shared. Everybody has to have a unique address. Yeah.
I guess I'm more so just interested in how like physically you can connect like the wires if there's only two pins on the bus. Okay.
The SDA and SCL don't go from one chip to one chip.
Okay.
It goes from one chip to many chips. So they all get access to the same data line. They all get access to the same clock line. So there's only one clock and one data for one bus. And they all share it, which is why like this line branches and goes to both of them. This line branches and goes to both. Other questions? Okay, good. Same thing was true with SPI. Different digital bus. Lots of wires being shared. How does SPI work? If it doesn't use addresses, what does it use? What? Those are the actual names for the data and clock line. Actually, those are both data lines. So one of those is a send line, master out, slave in. So that's the data line that goes from the controller to the responders. And the other one was master in, slave out.
Right.
Yeah.
There's like a chip select line.
There's a chip select line. So instead of using addresses, SPI has an individual wire that goes from the controller to all the chips. So that's why this says CS0, chip select 0, chip select 1, chip select 2, chip select 255. So like you can include as many as you want, but they have to have an individual line run to them, which is kind of a hassle. Yeah.
Is the chip select a special line or is it just a PWM line?
It's just a wire, digital line. Yeah, it's just a digital pin that flags.
So like on the Raspberry Pi, could it be any other GPIO pin?
It could be. Yeah. Although it might have, I suspect it has like specific lines that are designated as chip select lines, but I could be wrong about that.
And it would just like, if it wants to communicate to, let's say, chip 3, it would flag the 3 one to be on and all the others have to be off.
Right. It toggles it. It toggles it, I think, at the beginning and at the end.
What does like the GPIO mean?
It stands for general purpose input output pins. So
It could just be used for any, like, cause some of them like say GPIO, but then are like on the diagram, like, but then also have a specified like name after them.
yeah.
So then they're not, like, if they have a name, then they're not general purpose, or they're.
No, all those pins are either power, ground, or GPIO.
But then why are they also labeled like, oh, GPIO, and then it might be like the SDA line?
Some of those pins have multiple functions. So they can be set up to work as a data click SPI bus, or they can be set up to work as a general purpose digital pin. So that means if you set it up to work as a general purpose digital pin, you have control over it. You can say, go high, go low. What is it? Read it, is it high or low? So you can then like use it to do things. But if you use it as a bus line, you can't do, it can't be used as a digital pin at that point.
So like all GPIOs could theoretically, or wait, no, sorry, it would be the other, like, actually, okay, I get it, never mind.
Yeah, all GPIO pins serve as general purpose digital input output
It
pins.
could have an additional functionality.
But some of them have an additional designated function. That's why like the Pico has, I think, multiple versions of a single bus line, for example. It looked like it had multiple, for example, SDA I2C ones. So if you needed those digital pins and you couldn't afford to use them as a bus line, you could use a different bus line. Does that make sense? Yeah? Everybody tracking what I'm saying? You tracking? Yeah? Yes? Okay. All right, now's the time to ask questions. All right. This was our like little exercise we did with the BlinkM data sheet. That seemed to be very easy for you guys. That was cool. You guys remember full duplex and half duplex? That's a bus characteristic, whether it can talk and listen at the same time. And then the other thing that's kind of important is the communication speed. SPI is faster at about a megabit per second. CAN is faster, about megabit per second. USB depends on which version of USB you're using. And then I2C is lower, about 400 kilobits per second.
Why would we use I2C then, besides that it was around, I guess, early? I'm guessing it was around earlier.
It's that there's lots of chips that use it. So like if you want to, let's say you want to record from a pressure sensor, there's a good chance you'll be able to find that pressure sensor that uses an I2C bus. And then there's a good chance you'll be able to find a library or a driver that someone has built in Python for the Raspberry Pi for that sensor.
Nowadays, they're like moving away from I2C as they're making new chips, or
Not a ton. I mean, eventually it'll probably be phased out, but it's still used a lot. Yeah. It's still probably the most common. There isn't really a good like, hobbyist or DIY or bus solution. It's all pretty detailed like this. But I wouldn't be surprised if eventually someone did create something. Or USB-C just took over. That would be the other thing. Okay, so this was it for review. Oh, one more thing I want to say about communication. When you're building a robot and you end up building this control loop that runs usually as fast as it can. Ours is set at 200 hertz based on the reading frequency of what chip? IMU. So oftentimes that's not the case. Oftentimes there isn't a chip with a designated maximum frequency. So then the game is run everything as fast as you can. Oftentimes the thing that is the greatest bottleneck is communication on the bus. So you're running this loop, you're communicating with your sensors, and then you're going to do some math on that information and send some commands to motors or something. The communication bus to send all of your signals to get tell all your chips you want to get data from them, and the time it takes them to send that back. If you space that out over the bus, the time it takes, if they can do a megabit per second, you look at all the bits that are being communicated, that's the greatest bottleneck generally. So communication ends up being like a big part of high-speed robotics. Does that make sense? How many bits do you think it takes to ask the IMU to send its data? I don't know the answer to this, but I'm going to ballpark it.
Just to ask.
How about the full transmission? You ask for data, it sends its data. How many bits do you think that is? You would just like ballpark.
64.
I'm going to say it's like 150, if I had to guess. Because it doesn't just send the information, which are probably 16-bit numbers. So we have 6 16-bit numbers. And there's a bunch of header, footer, communication infrastructure around those messages. So if you actually count the bits, there's a ton of information that goes across the bus. That's why it's slow, or can be slow. Does that make sense? That would be a good homework question. It would be how many bits are sent total. I didn't put that on the homework, but it would be a good one. All right, so we're gonna do our actual content. We're just gonna go over 2 small things, and then we're gonna break and go back to the robotics building. We're gonna talk about Omni wheels. Omni wheels are a really a neat invention, and this is the first time I've ever used them is in this class. They're really cool. I've always wanted to use them, but I never had a chance to. So they're cool. The way they work is that you have a wheel with a bunch of rollers that can rotate perpendicular to the plane of contact. What's kind of really cool is these wheels were invented in 1919. That's the US patent for it. It's crazy. But the wheels move perpendicular to the turning direction. In some configurations, Omni wheels enable full specification of the position and orientation. Of a robot. We call this holonomic motion. What do I mean by in some configurations, Omni wheels enable full specification of position and orientation? What is a version of Omni wheels that does not provide? Yeah.
They're all parallel, the robot couldn't turn.
They're all parallel to each other. So if you had a a wheel with 4 Omni wheels, at each one in the corners, like a car, then it can't specify all position and orientation.
Unless the wheels themselves were able to like turn, right?
Say that again?
Unless the wheels themselves were on like some like
Unless the wheels
differential.
themselves were able to. Yeah, in this case, we're not thinking about that.
Like the Hummer EV, like the new Hummer that was released that can like crab walk almost, but
I
then it can
haven't, I
also
haven't seen that.
it's pretty cool.
Is it?
Yeah,
So
it can
they-
like go omnidirect, I guess technically. Like it doesn't have wheels like that, but it somehow is able to like I don't know how it works, but like it can actually like move laterally along with like turning.
Nice.
Some sort of swerve.
I did see, as I was kind of looking this stuff up for creating this lecture, a version where someone created a wheel for a car that had it was a regular like rim and a tire, but that tire was not, a U-shaped tire that goes into a rim like normal. It was a kind of a donut, so it was a circle that went all the way around, and then it had motors inside the rim that would basically spin and rotate this inner tube around, and the car could move side by side. It was insane looking. So that's cool. Totally different type of Omni wheel. But okay, right. So if we put them like this, if we put our orient our Omni wheels like this, do we have holonomic motion? Yes, we do. Okay. So as a result of this idea, the Omni wheels are usually placed in an angled configuration. They have rolling contact on the ball and sliding contact between the wheel and roller. And there's kind of many different versions of Omni wheels. At one point I had a version of the slide that showed a bunch of examples, but there are lots of different sizes and shapes and roller shapes. So we have a version that is not as smooth as this. Ours has like a lot of radial deviation around it. That's gonna be kind of a challenge because it makes the whole system vibrate. So that's not ideal. Like these types of wheels I think would be better. I think they're like less radial deviation. So yeah, this has been an example of like different steering commands for Omni wheels kind of in our general configuration. I thought this was cool and easy to interpret. So in this, gray is, for some reason, there should be like a legend here. I don't know why. Gray is stationary, red is moving, and moving with the direction of the arrow. So this hopefully is kind of intuitive to you. And this links back to exactly what we did in lab. A different type of wheel, something called mecanum wheels. These are neat also. They also use rollers located around the circumference of the wheel, but those rollers are pitched at a 45-degree angle. And you can kind of see that through here. These wheels, mecanum wheels, are generally used for four-wheel operation where the wheels are parallel to each other. So that's the idea. These you see a lot of robots in the Ford building that use these. They're pretty neat. So they enable holonomic motion also. And they provide lateral motion with canted rollers. The way this works is now each component of torque creates forces in two directions. So it provides two known components of force. So what this ends up being is a bunch of algebra or geometry to kind of solve these equations. They're not too difficult. So these are force vectors. And this tells you kind of the mapping, how to make it do all sorts of different movement profiles. One thing that I think that you can do if you wanted to is use this as kind of as a dictionary, and you can create almost any motion path by summing linear combinations of these motion profiles. So it's kind of neat. Now I have like kind of a question or example. What I want you guys to do is set up the equations. We're not going to solve them. We're just going to set them up. I want to set up the equations for that robot to move at an angle of 80 degrees off the x-axis at 1 meter per second. What do we need? If we were trying to control this, what would we need for commands? Or I guess, which what I'm trying to get you to solve here is the velocity command. What is the velocity command for each wheel to move it in an angle at 80 degrees and no rotation of the body? So it's only going to move straight up and to the right a tiny bit. Don't let it rotate. How would we set this up? Yeah.
We know that the velocities of motor 2 and motor 3 have to be equal and opposite. But opposite.
Isn't it also, it's not going straight up though, right? So,
Yeah, I would say like, since it's
Oh,
canted,
sorry,
it's
I was
not
doing-
going to
sorry, I was
be.
doing it going directly to the right, sorry.
Yeah, it's going to be canted at an 80-degree angle. So they're going to be close, but they're not going to be exactly right. So we need some equations. How many unknowns do we have? 3. So we need 3 equations. What equations do you think we need to do to solve this? Yeah.
An equation relating the velocity of each motor to the output of how it would affect the robot.
Yeah, I think that's right. So another way we could think about that is let's think about the tangential velocity applied by these wheels. And then we want the sum of those tangential velocities to have a component that moves mostly up and tiny bit to the right. So we have the kind of trigonometric sine and cosine components of that velocity, which we know. Now we have 3 unknowns. We need one more equation. What's the other equation? Yeah.
have to do with like the torque to like tangential velocity like equation, like converting like a torque of the motor into tangential velocity.
No, so I think actually like that's going to end up not mattering because they're going to be related by the radius of the wheel. So that will end up, I think, falling out. So there's 2 equations that govern as components of velocity in the plane. So a component in x and a component in y. The 3rd equation says that you don't want it rotating. So what does that mean? If we don't want it rotating, how do we, like what constraint is that? If we don't want it rotating, what's true? Means the velocities, if we look at the tangential velocities, and the motion they provide around the body center, they should sum to 0. There should be kind of a rotation around its body. Since those are all located at the same distance, I think I can say that as the velocity of motor 1, the velocity of motor 2, and the velocity of motor 3 all sum to 0. Do you agree with that? Okay, so now there's one more thing we haven't talked about, which is getting these angles. You're going to need to know those angles. What I'd like to do for 10 minutes before we break is for you guys to actually get these equations. Try to write these equations. There's 3 of them. One of them I just gave you. Find these angles, write those equations, and I'm going to write them as well. And we'll see if we get the same thing.
I'm a little bit confused about the sum to 0 thing, because like how is it like if the net velocity is 0, then how is it moving? I guess like I get like conceptually a little bit, but also then like how is it gonna have any direction of motion if the sum of the velocities is 0?
It's not really, I mean, it ended up being the sum of the velocities is 0, but it's really the radius times the component of velocity, the perpendicular to that, plus the radius times its velocity perpendicular. So radius times its velocity perpendicular. So the sum of their tangential velocities should equal 0 in both the x and y planes.
But don't you need like components along the x and y direction in order for it to like translate? And
Yeah, this is not supposed to be, I mean, it's really about a rotational concept. For now, right, let me step that back out and get the expression that's not as reduced and then go from there. For now, try to get these, I want you guys to try to write these equations. Is there a question? Yeah.
Is the x-axis like going on the right or is that?
Axis.
So you, this is those components, and next thing, so what's all those components. That makes sense, we're gonna split the 1 meter per second, meters components. And then 3 meters to some.
Gives me velocity times cosine of something. Plus velocity times like cosine or something.
Yes.
That's- okay.
Yeah, it should look like that.
Yeah, okay.
Yep, two people, tree expressions.
Perfect.
You get something like this. You get theta 2, 20 degrees. Theta 3, 240 degrees. So we just want the components of the 3 velocities to be equal. This should say that it doesn't rotate. Did you guys get this? So like not maybe as hard as it seems. So working with Omni wheels is pretty straightforward. You just have to do the kinematics and geometry, but it's not too difficult. Yeah.
The only part I don't see, how did you get theta 2 and theta 3?
How did I get them?
Yeah.
I got them by thinking, what is this angle? That's 120. And I'm either
Oh, from the 0. Okay.
Yeah, 240 minus
Okay.
90. Yeah, same thing here.
Okay.
Cool? Okay, so this is generally the content that I wanted to share with you today, which is basically a review / Omni wheels. This kind of shows us where we are. We've done Omni wheels of communication now. We're basically left with controls. We have balance control and steering. We're gonna start with balance. And then I'd like to stop now or talk you through the homework questions, and then break, let you guys have a little extra time to work on your ball bots. What's that sound? You hear that?
Backing up.
Okay, got it. Do you want me to quickly go through the homework questions? Okay.
Yes.
Okay. Okay, homework 4, posted. Question 1. This question is about the alignment of the efficiency and alignment of the y-axis and the kind of motor concept. What I want you to do, or at least like track, is movement of the ballbot will now be more efficient in certain directions than in others because of the way motion is broken down into the movement across the three wheels. So what I want you to do is to quantify that relationship. What I'm asking for is a polar function of loss around the circle. The loss is I squared R. So I can pick a torque, say I'm gonna, or a force or torque on this movement direction, calculate the loss, and then move to a different direction, calculate the loss. You should be able to get a polar plot of loss for a fixed torque. And then the minimum of that polar plot is the most efficient direction. Does that make sense? What direction will be the most efficient direction? You should already, potentially already know the answer to this. Moving along the y-axis. Okay, so quantitative, you don't necessarily need to provide a plot, but that is how I would do it if I were solving it. I'm gonna kind of leave it up to you, but you have to be quantitative. So I need a quantitative explanation for that. 2, some torque conversions, it's not hard. 3 is to design a data acquisition system. In this question, you're building a system that uses a gripper, a robot gripper, and then in order to sense the grip strength, you're using something called a force-sensitive resistor, which is what this is. The way these work is their resistance changes when pressure is applied across that pad. So you were given this question and the data sheet for this resistor. And what I want you to do is it says your goal is to design a system that outputs 1 volt at 1 kilogram, which can be sensed through a data acquisition system. Data acquisition system is 16-bit with a 0 to 10 volt range. And then I want you to answer some questions here. Design the circuit. I would implement this, which is not hard, because it's not as challenging as maybe it seems. What would be the other resistance in the circuit? The circuit is a voltage divider. So what is the paired resistance that you would need? And really, that's kind of the question, is choosing that resistance such that you get 1 volt at 1 kilogram. Make sense? Question 4 is to define the Nyquist criterion, explain why it matters, find a reference. Really just know what the Nyquist criterion is. Question 5 involves an experiment with your ballbot. So this question can be worked together with your partner. What I'm asking you to do in this question is to make the ballbot spin about its vertical axis. So if we don't have the balance controller running by this time, you'll have to hold it with its ferret leash so to balance it for it. But then what I want you to do is apply torque to the motors and make it spin. What I want you to do is get the mapping from motor duty cycle to angular velocity or angular motion. I want you to determine that angular motion using the IMU, the vertical axis. I think that you guys have access to the vertical axis in the gyro, but if you don't, you might have to change the firmware to allow that, and then also calculate it with the encoders, just like in your lab. Does that make sense? So your answer, this plot that you're going to create, should look like 2 lines that describe angular velocity as a function of motor torque. The 2 lines should represent the 2 ways to calculate it, by the encoders or by the IMU. Make sense? Now you can ask questions if you're unclear. And then the last 2 questions are just simple. This is a decimal, hexadecimal binary conversion question, and this is just further read that BlinkM data sheet, provide the actual communication structure. Cool, questions? So this has a handful of very, very easy questions and a handful of very hard questions, or at least very time-consuming questions. But the intent of this is also to get you guys working with your ballbots more. Yeah.
For question 5, when we're doing the plotting and the torque and all that, should we use the Python script we were given yesterday?
You're welcome to use whatever you would like to use. You're welcome to use that Python script, but you'd have to modify it.
Okay.
before we adjust it. It is possible that, I have to go back and check, but it's possible that that we don't provide the vertical axis gyro information. I have to check. Or at least like if you try to do that and you're like, we don't have this in our, where can you guys find all the function variables? You remember? What? It's the states, and where was, that was in a file. Message defs, I think. Message def.py. So if you look at message defs and it doesn't have the vertical axis information, then we'll have to update that, yeah.
So like for question 5 again, like it's saying taking like duty cycles to go to like the rotational velocity. Like since we were already provided like in that Python script that we were working with, like we could just say, all right, we just want like torque that causes z direction of motion. Like
that's fine too. Doesn't matter. You're saying it says to use a duty cycle and you're providing a torque. Doesn't matter. I'm happy they're both are equivalent to be. Just has to be. Yeah, you should be able to control it and measure those things. Yeah.
What does it mean when it says like the perform 3 tests at each condition? What are the different conditions?
Different velocities.
Okay.
So like you wouldn't just measure it once.
Okay.
You would measure it 3 times to get an understanding for how different the data are trial to trial.
Okay.
They end up with a distribution of data.
And how many different
Velocities? Did it?
It says like 4 to 8 points. Enough to really to capture this relationship.
Okay.
Make sense? Any more questions? Okay, so I'm gonna head back over to robotics. I have office hours starting soon. Come to office hours, work on your homework, work with your partner. We're gonna break. It gives you a little extra time to work with your team and your ballbot. I will be in touch with you about the plan for Tuesday. I should just think about whether that should just be ballbot workday or that should be starting control. Because otherwise, next week's lab, we might want to begin doing the control in lab, which means we have to talk about it on Tuesday. But I'd rather, but for that, I would rather give you time to work on your ballbots. How many of you feel right now tell me how you're feeling with working with the ballbot? I think there's a really large spread, as I see it, in the class, and sort of like skill level and progress. And that's totally okay. And like that's, especially like with a new robotics department, that's gonna be how it happens. Like everyone's gonna be distributed across the workload. So that I was expecting. But what I don't want is for students, especially those that are on like the further and back on the workload, to just not get the experience of like building and working with robots out of this class. And that's what I'm afraid is that we're just not spending enough time with the ballbots. How are you guys feeling about working with the ballbots? What is so like when I'm sort of imagining most answers would look something like this. What can we do to make that better? Is it more time? Is it more instructions? Are the tasks too big? Like, if you guys have thoughts about this, this is really helpful for me to know. Yeah.
I mean, I think a lot of the stuff up until this point has been like not as like directly, like a lot of it is like theoretical stuff like in lecture, but I think, I don't know, especially as we get into control and like we're testing, I assume it's gonna be more.
It's gonna be more hands-on.
Yeah.
But the way the class is set up is like right now we do tons of lecture content and lab is long, it's 2 hours, but we don't get very far. Like that 2 hours goes by very fast. So that's sort of the issue. Like, so if we keep going as it is, we're gonna learn lots more lecture content. And what I'm afraid is we're further ahead on lecture content and we're behind on hands-on interaction. Control will help with this, but if there's a more fundamental change that we need to make or that I need to make with the structure of the class, like that, I just wanna know that if that's true.
Maybe just like you were saying, like every once in a while, like dedicating one of the lecture slots to like just going and working in lab. Yeah.
And if I do that, you guys will come and work. What I'm afraid is if I do that, no one will show up. Like it'll just be me and the class will really just be like a wasted class period.
Since this is mandatory attendance, you can just make it the same. You have to show up over there or else you don't.
Okay.
Or do like how we do want to do quizzes and like
Something along those lines.
Probably. Say that again, sorry.
No, I was just saying like how we, like sometimes you'll do quizzes like to check for attendance.
Yeah.
Like similar concept, like,
Okay.
but not actually like doing a quiz, just like attendance.
Attendance? Okay, that sounds good, yeah.
I guess instead of having longer problem sets for homework, maybe having like lab-driven tasks in between. Because like, I don't know, I see myself spending a lot of time on this problem set, but maybe I can focus some of my time getting ahead on lab or like completing more like things that would get us farther ahead for next lab.
So you're saying
Like
labs should be more defined in what should be accomplished in that lab.
Like for example, last week's lab we worked on the ball kinematics. Maybe that could be assigned as a homework. So then the next lab, like
Yeah,
we're still moving ahead in our ballbot rather than like a theoretical.
yeah. I think there probably should be deliverables for lab that work their way into homeworks or assignments. I think that's probably better. That's sort of what I tried to start with this one, the block creation, but I'm with you. Okay. That's helpful. Keep thinking about this and let me know kind of how it's going. So far I'm really pleased with this class. I think you guys are doing great. I think you're learning a ton. I think you're learning both theoretical and hands-on skill. I just want to optimize this class to achieve its goals. But I am actually like really excited about how this class has gone so far. Yeah.
Yeah, I was just gonna second that because I think it's also like it's really important to like have the expectation that we're like outside of class, outside of lab.
Yeah.
We will be like spending some time with the ball because I think it's just unrealistic to like have enough time
in lab
structured for us to like get the familiarity that we want to get. So I think like definitely the lab assignments is like a good way to just make sure that our groups are actually meeting and like doing stuff outside of the lab.
But also balancing with homework assignments.
Okay. Yeah, that makes sense. I think we can do this. So let's talk about this week. So this week, like one thing we could do, or really next week, next lab, we could begin control, balance control. That's kind of like where I think we're headed unless we change that course. What we could do, that would mean we do lecture content on Tuesday about balance control. I'm gonna be able to give some of the lecture back to you, but that usually ends up being less time than I want it to be. Like today, it's 1:05 already. So one option would be go over content on Tuesday, do control on Wednesday. Another option is have Tuesday be like a work on your ballbot day, and then that would mean that there's very little infrastructure around lab. But that would mean lab is basically more work on your ballbot, work on the homework, like get everything done up to this point if you haven't gotten it done. Lab 8, 9. With that, like what do you think of that plan?
I think especially with like the midterm coming up, that could be pretty helpful because like organizing time between studying, homework, and ballbot lab. At least like I know for like this week it would be pretty nice to like get hands-on time with the ballbot still being in class where then I can also do homework another time because like there are other exams for other classes too. So like it provides a little bit more balance.
Okay. What do you guys, everybody else, do you think that?
Yeah.
Okay, so maybe the plan will be Tuesday, work on ballbots, which means me and leading the lab space. Wednesday is essentially more of the same, so more of that. Both of those times I would be there, and hopefully even maybe Gunther. And then we would do review on Thursday, then exam the following Tuesday. So then we're still going to be at the lab again without having gone over control. So let me think about that. I think we'll probably do that. I just might have to take the first part of that lab and talk you through some of the control stuff that we're going to start. So it might have some electrical content in the beginning of it. But I'm with you that I don't want the next week or week and a half with the exam to be really crunched. So we have time, still have time to work on control. Yeah.
It could also be like if we want to start like doing lecture and lab, doing the lecture, like if we're gonna put a portion of the work time during the lecture, just always meeting in there because then like it saves the commute time of like walking in between or something.
That makes sense. Yeah. I don't really know access to that room during this class time. Gotcha. So that's the thing that just sort that out and figure out how to make sure that I can reserve it. But okay, all right, so then this sounds good. Let me give that some thought.
That note of having lecture in there,
yeah,
I like that a lot, but that room I don't think is very well suited to lecture.
Right.
So there's a lot of other space in the building maybe we could find an open room or like one of the lounge areas, somewhere that's more well suited for a lecture style.
Yeah, it's not conducive to election, I agree. Okay, anything else? I think we can pause here. I'll send an announcement about Tuesday for sure. And I'm planning on giving it back to you guys. It's time to work on your ball bots and do it in the lab room.